A radioactive nuclide X decays in a single stage to stable nuclide R, and Y decays in a single stage to stable nuclide S. When a rock formed, it contains equal numbers of atoms of all four nuclides, so X to Y to R to S would be 1, 1, 1, 1. The half-life of X is T years, and the half-life of Y is 2T years. What's the value of the number of atoms of R over the number of atoms of S at a time 4T years after the rock is formed? So if we notice, this is 4 times the half-life of X, and this is 2 times the half-life of Y. So how much X would be left? Well, if it decayed in 4 half-lives, there'd be 1 over 2 to the 4, kind of half multiplied by half 4 times. And then there'd be 1 over 2 squared for Y, because it's done half and then another half in that time. So R and S would have gained these amounts. So how can we work that out? Well, if X decayed to 1 over 16, that means 15 over 16 became R. So R now has 1 plus the 15 over 16 that came from X, which is 31 over 16. Now Y must have gone to a quarter, so that means 3 over 4 became S. That means 1 plus 3 over 4, because there were 1 S originally, becomes 7 over 4. So R over S would equal 31 over 16, and then dividing by 7 over 4, so that's the same as multiplying by 4 over 7. Again, don't multiply 31 by 4 here, because we notice a cancellation between 16 and 4. It gives us the 4 on the bottom. So we have 4 times 7 on the bottom and 31 on the top. So our answer is 31 over 28, which is C. So 31 over 28 is the answer here. You might be thinking, how come we got fractional answers here? Well, if you think about it, there'd be large collections of atoms. So I've just gone for a ratio of 1 to 1 to 1 to 1. So if you wanted to do maybe 100 million or billion of them, and then you would have got whole numbers if that's easier for you to understand. But because it's just ratios, it doesn't really matter what numbers we use here. So let me know if you have any questions, but hopefully that clarifies how to do this problem.